So in terms of agenda, I want to start off kind of talking about how we got here, why I think container networking is important, something we should be paying attention to. Then I'm going to get into some of the technical stuff. I want to go through some definitions that I think are relevant, talk about the mechanics, focusing sort of on the primitives of how we connect a service in a container to the upstream network. And then we'll talk about some of the Docker networking built-in options. And then we're going to touch on some of the third-party plugins, but more with a focus of sort of how they integrate with a container runtime, more than actually how they operate necessarily. And then if I've got time, I've got some kind of looking forward statements, but if I run out of time, we'll just jump to questions. So one of the things I like to do when I start looking at a new piece of technology is I like to spend some time listening to talks and presentations given by folks who are using it in production at scale. And if you do that with containers, one of the things you'll find is that when they talk about their challenges, it doesn't seem to matter who they are, how big they are, is that they bring up networking. Container networking is hard. And I think it's hard because this is a new paradigm for us. If you're a follower of sort of the belief that we started with bare metal servers, then moved to VMs, and now we're with containers, when we made the move from bare metal to VMs, I'm going to suggest it wasn't that big of a change for the application teams. They were still using the same base construct to deliver the application. But with the move to containers, it's a completely different construct for them. And one of the things people like to do, right or wrong, when these iterations occur is they like to attempt to compare the current iteration to the new iteration. And so if you're out there researching containers, one of the things you'll find is there are a lot of blog posts and stuff about VM versus container, right? People want to make that comparison. And I'm not sure if that's a completely worthwhile exercise all the time because they are so different. But if we attempt to do that from a networking perspective, they do actually have some things in common. Namely, a VM and a container typically represent an IP endpoint. But that's sort of where the similarities end. And there are many more differences, and those differences, while not necessarily network attributes, do impact us on the network side. For instance, size. We know that a VM is an abstraction of a physical machine, meaning it's quite large. But when we talk about containers and container images, we're talking about them in terms of megabytes or tens of megabytes. So they're considerably smaller. Smaller means we can have more of them. More of them means we have more IP endpoints to deal with. I will point out here, microservice architectures tend to come up a lot when you talk about containers. They are not directly linked. You can have microservices without containers. But if you do have a microservice architecture that's based on containers, it's interesting to think about the fact that previously you had a server that was providing many services on one IP. If you have a container-based microservice architecture, every one of those services potentially has its own IP address, right? So that gives you sort of an idea of the scale out that we're seeing in terms of IP endpoints. Secondly, differences. Ephemeral, if you've talked to anyone that's been dealing with containers, you've likely heard the term. Folks like to use it to describe the fact that containers can be dynamic. That is, they can come and go. So not only do we have more of these IP endpoints, but they're now also more dynamic in nature, right? So if we view these more as generic network challenges rather than differences, do they sound sort of familiar to any of you? Perhaps things you've tried to solve in the past before, right? Scale out dynamic endpoints. Yeah, I think they should. And I think they do because I think this is just another iteration of problems we've attempted to solve at other network abstraction layers, right? Lower levels. So let's talk about those layers for a second. The problem with talking about networking abstractions in the terms of layers is it tends to give us this false sense of autonomy. Folks who are especially outside of network engineering sometimes get in their heads that the functionality that exists within a given abstraction is the only thing they need to worry about, right? And we know that that's not true. We know that higher level networking abstractions are typically built on lower level networking abstractions. And more importantly, higher level networking abstractions or things that exist there probably need to talk to things at lower level networking abstractions, right? We saw this with virtual machines. When virtualized networking came, the real challenge, in my opinion, there was attempting to bridge the overlay or whatever construct you were using back to the physical network, because we had to do that at some point. So it's important when we talk about containers to talk about them less as a transition and more of as another building block, I think, on top of existing things. So if we view a container as an object that lives in an operating system, that operating system still has to live somewhere. So we have these lower level building blocks, right? So those could be a physical bare metal server or a virtual machine. And each of these other building blocks has its own networking model, its own networking abstraction attributes, right? So for instance, with a physical host, we know that most of the interesting networking typically happens upstream, right, off of the host on the network. Virtual machines, we've seen a huge explosion in the amount of networking happening in the virtualization layer on the host itself. But with containers, the interesting networking stuff is happening in the guest operating system. So I'm going to suggest, I mean, most of us probably traditional network engineers, that's a space we probably haven't played around a lot in. You know, siloed organizations. The operating system was typically owned by another team, right? Probably an infrastructure, but not network engineering specifically. And so this is putting us much closer to the app than I think we've ever been before, which I think is a good thing. I think we need to be there to start delivering networks for these applications. But it also means we're starting to blur the lines of ownership a little bit in regards to who manages it, who owns it, who's going to maintain it, to configure the network. So that's stuff that we're going to have to sort out. I don't know why this isn't. Okay, so I was trying to think of how to summarize my points early on here. And I was having some difficulty doing it. And this tweet from Keith Morris came across my Twitter feed, and he says, the point is new tech like containers won't help if you don't have the fundamentals right. And I think he's probably talking about maybe software development fundamentals, but I think we can apply this to pretty much anything in regards to new technology. For instance, could the fundamentals here mean existing infrastructure? Are we good at those lower level building blocks that we're building on top of? Because if we're not, I think it's going to be really hard to define a new abstraction on top of that. Could the fundamentals mean cross-discipline collaboration? Are we good with working with the other teams, not just in infrastructure, like we started to do with virtualized networking, but also with the app teams now, right? I think networking is becoming less about providing generalized copy-paste infrastructure. You know, we're not just providing ping anymore, right? We have to provide a network that's designed for the application to scale the way it needs to. So my point with all of this is sort of obvious, and I think we're all familiar with it, but the point is, you know, new things rely on old things. So as we look at these new abstraction layers and these new building blocks, I think it's important to know your options. We have the experience in kind of bridging these layers together, and this is just another building block sort of on top of that. So that's sort of the end of my initial intro rant. Before I get into the technical stuff, I have a quick disclaimer. I like to say Docker is the Kleenex of containers. There's not a negative connotation to that. It's just the fact that when you think containers, you probably think Docker. That's just because they were really the first project to put it all together. So when we talk about container networking for the rest of the talk, it will be in conjunction with Docker. But they are not the only container runtime out there. There are some other pretty popular ones. Rocket by the folks over at CoreOS is becoming pretty popular. But regardless of which one you use, the networking implementation is going to be largely the same. That is, on a Linux system, they're using base Linux networking constructs to deliver container networking. So different runtimes might do it slightly differently. They might use the contracts or constructs in a slightly different fashion, but it is largely the same. Lastly, it might come up, but container orchestration is a huge topic. It's massive. Networking is certainly a huge part of that. But today, again, I'm going to focus sort of on the primitives of delivering a container service to the upstream network. So defining a container. You guys can read this definition. I copied and pasted it off the Docker website. It does a nice job of defining what a container image is. But from a network perspective, we already said that a container represents an IP endpoint, right? But more importantly, a container represents, in the Linux system, a network namespace. So who here knows what a network namespace is? Okay, some people, that's good, okay. So what is a network namespace? Namespaces have existed in Linux for quite a while. They have the goal to limit or scope what you or a process can see. So if we try to compare that to more traditional networking, the closest comparison would probably be a VRF, but it's not quite a VRF. We know VRFs provide us layer 3 isolation in most cases. Network namespaces are complete and total isolation. So everything inside the namespace, interfaces, physical and virtual, IP addresses, routing table entries, sockets, everything. It's a complete isolation, right? So if I have a host that has 2 network interfaces, I install Linux on it, they will both exist in what's called a default or root namespace. I could then later move one of those to a different namespace, at which point the default namespace would not know it exists anymore. So interfaces can only live in one at a time. So that sort of makes sense from a base perspective. Okay. So now we have a problem, right? Because I just described that a container is a network namespace, and network namespaces are completely isolated. So if we have a server that's running a container, and we have to assume that the upstream network knows how to reach the server, otherwise none of this is going to work. So the server has an IP of 10.10.10.1. We assume the upstream network knows how to get to it, but we want to consume the service that's in the container itself. So if it's completely isolated, How do we do that? The solution comes in the terms of VETH pairs, and if you work with Linux networking for any period of time, this is a construct you're going to see over and over again. It's used widely. It's best to think of it as sort of the virtual patch cable of Linux networking. When you define them, they always come in pairs. You'll get two interfaces when you define them, and the assumption is what comes in one interface will come out the other, right? It's just like a patch cable. Either end can be thought of, there are sort of two main modes of operation, at least with containers. And I like to think of them as layer 2 and layer 3. These are not Linux man page definitions. You will not see them defined this way. It's just how I think of them to help me process how they work. In layer 2 mode, we attach one end of the VETH pair to a bridge. So you can think of a Linux bridge sort of as a layer 2 access switch with all the ports in the same VLAN. And I can connect a bunch of these VETH pairs, and then they would be in the same broadcast domain. They'd all be able to talk to one another. The other option is layer 3, in which case we actually assign an IP address to the end of the VETH pair. And this gives us layer 3 reachability. It's sort of hard to explain, but we'll see in the example why this is important. The reason we're talking about VETH pairs, though, is they have an interesting attribute that they can bridge network namespaces. So this is a means for us to break that isolation and connect into an isolated network namespace from the default or root namespace. So our solution here is we create a bridge on the host. We do this because there's a possibility we want many containers, so we want a common connection point. We give that an IP address, in this case 10.15.20.1, let's call it a /24. And then we create a VETH pair. We put one end of it connected in that layer 2 fashion to the bridge. We take the other end of it, throw it over the wall into the network namespace of the container. And this IP address we see here in the container of ETH0, the 10.15.20.10, is actually the other end of the VETH pair. That's just assigned in that layer 3 fashion I described. There's no reason to have other constructs in the container to put the IP in and then do more connections. So having the option to assign an IP address directly to a VETH pair is sort of our best option. So I was going to do a real demo, but those never work for me. So I apologize for the copy-paste slides here. But in real life, this is a Ubuntu 16.04 host I built. It's completely brand new. The only thing I've done is downloaded Docker Engine and started the service. So if we look at the interfaces on the host, we'll see that there's a Docker 0 interface. It has an IP of 172.17.0.1. It's a /16. And if we look at our routing table, we see what we expect. The host has a default route pointing out its ENS32, that's its physical interface. And then we see two kernel routes for the directly connected subnets of the IPs it has. Starting a container is pretty straightforward. We say Docker run. We pass in a couple parameters, namely -d tells it to run as a service or a daemon in the background. We give it a name to make it easily identifiable, and then we specify a container image name. In this case, this is a new install. Docker doesn't have the image cached locally, so it will download it and execute it. And then we can use Docker PS to confirm that the container is actually running. Now, if we go back after we run a container and we look at our interfaces, we see we have a new one. There's this VETH 32CD045. And I'm guessing that you're guessing that by that naming standard, this is part of a VETH pair. We can also see that this interface doesn't have an IP address on it, which is sort of an indication that this might be assigned in that layer 2 fashion I described. And we can also then look in the container itself. Docker allows you with the docker exec subcommand to run commands within the container's namespace. So we'll run the same commands. We'll do an if config. We see the container has an ETH0 interface. It's got an IP on the same subnet as our Docker 0 bridge, .2. And if we look at the routing table, we'll see it has a default route pointing at the Docker 0 bridge, 172.17.0.1. So this is our connectivity method from the container back to the default root namespace on the host. So I mean, I just told you that, but we can actually prove it too. If we use the IP route 2 toolset commands, we can use the IP link command to get a little more information about the link itself. In this case, in the top box, you'll see in the green bubble, we're getting the full name of the interface, which is actually VETH32CD045 at if 10. The at tells us we're working with a VETH pair. The 10 specifies the index number of the other side of the VETH pair. So if we run that same command with Docker exec again within the container, we say it's really ETH0 at if 11, right? But it has an index of 10. So that's how we're matching up the ends of the VETH pair. And then if we look back on the host, we'll see that that index number matches up with the VETH pair in the container itself. This works in Docker because Docker initiates the VETH pairs from within the default namespace, ensuring the numbers are unique, and then later moves one into the container's namespace. With other runtimes, you might need to do the verification a little bit differently. I'll also point out in the blue box, we see the host side VETH pair interface lists a master of Docker 0. This tells us that it is in fact assigned in that layer 2 fashion, and it is assigned to the Docker 0 bridge. So that's the full connection path for us. Does that sort of make sense from a base networking perspective? Okay. So now what? At this point, we have an interface on the host, which is on the same subnet as the container. So there'll be IP reachability there, right? We can do normal things like we expect, like ARP. But the subnet these containers are on is not known to the upstream network. 172.17.00/16, nobody knows about it, right? So we have two problems to solve. The first is a container talking to the external network, right? There's an assumption that we're going to want to return traffic back up to the upstream network, or maybe even reach out to do things from the container. And the second is accessing services in the container from the external network itself, or the upstream network. The container to external is actually pretty straightforward. We saw that in our container we had a default route pointing at the Docker 0 bridge. That's how we achieve getting traffic back into the default or root namespace. Once we're there, Docker by default will create a set of IP tables or net filter. I use those terms interchangeably, I probably shouldn't. But it'll create rules in the default or root namespace to allow the traffic to be actually outbound masqueraded or source netted behind the IP. Again, we're working with the assumption here that the host interfaces are known to the upstream network, right? So Docker has to make an assumption that if that's the case, it has to hide the traffic behind an IP that it knows the upstream network knows how to get to. So you can see as the traffic traverses out of the container, gets in the root namespace, we will do a source net. The actual rule here is at the bottom. This is what Docker inserts. It's part of the NAT table. Part of the post routing chain, we say if source Docker 0 bridge, if not going out Docker 0 bridge, we jump to a target of masquerade. Masquerade will do a route lookup, it'll determine the egress interface and source net the traffic behind that IP. So sort of just like how we access stuff on the internet, right? We're just hiding the traffic behind a known IP address. External to container is a little bit different. It is non-default with Docker. And it relies on a system of port mapping. So again, if we are under the impression that we have to use known IPs to achieve this connectivity, we have to do the same thing, but just in reverse. So what Docker does is picks random high ports and maps them into the real ports of the container. So Docker does this through a system of what they call exposed and published ports. Exposing the port, there's not actually anything that happens with that. There's sort of a misconception with it. Exposing the port means that when I build a Docker image with a Docker file, I'm putting in sort of metadata flags that tell the container runtime later on what ports the service offers, or what ports the container offers a service on. So later, when I run that image, the Docker container runtime can read that metadata and say, okay, I know you want to offer a service on port 80, for instance. I can then tell Docker with the uppercase -p flag to actually publish the ports. Publishing the ports is the actual means of it creating network connectivity for the container. So in this case, it would pick a random high port, call it 32768, and it would map it into the real port and IP of the container. So if you wanted to access, we'll see it on the next slide, but if you wanted to access a web server on the container, you might do so through 10.10.10.1 port 32768, and it would take care of the destination net for you. There's also an option of doing it manually, the lowercase p flag. In this case, I'm allowed to pick both the host port I want to use as well as the port of the container itself. So if I didn't specify the expose command, or if I want to override it or specify additional ones, I can manually do it at container initiation as well. So this looks sort of like what I just described. It's a destination net. Inbound traffic would come in to the host IP at 10.10.10.1, go to port 32768. It would be a DNAT to the container IP and port that the service is actually offered on. And again, we can see the real rules here at the bottom. Again, we're in the NAT table, pre-routing chain, address type, destination type local. That's looking for traffic that's destined to an IP that the host owns. And then we jump to a custom chain of Docker. We say, if not going into the Docker 0 bridge, if TCP, if the correct port, we jump to a target of DNAT, which is a terminating target, and we'll perform the destination NAT to the right IP and port. So does that make sense, sort of in and out? That's why Docker was super popular early on, because developers could use it without, I guess, essentially telling network engineering what they were doing, right? They could present services on their own. So all the functionality we've seen up to this point represents the default in Docker. It's the Docker bridge mode. All of the containers will be attached to the same bridge, in this case the Docker 0 bridge. And this means that they'll all use the Docker Zero Bridge as kind of a common connection point and gateway. That'll be their default route. This also means by default, just normal networking here, all the containers could talk to one another, right? They could ARP for each other's IPs and communicate. There's an interesting option worth bringing up called ICC mode. It stands for inter-container connectivity. It's by default set to true. It's a service level parameter. We could change that to false, in which case Docker would prevent the containers from talking to one another directly, but still allow individual container access for publish port and egress communication. So there are a couple other built-in options. These have existed, I think, maybe since the beginning, at least since I've been looking at it. Host mode is sort of an interesting one. There was a thought initially that it was a more performant means, because what it does is it, instead of creating a network namespace for the container, it instead puts the container in the host default or root network namespace. This obviously is a little bit of a security concern because it's giving the container access to everything that the host or default root network namespace has access to. So this is used in some cases where we need that access. So if you're running a container that's doing something at the network level, sometimes you have to run it in host mode. It was thought to be more performant because we were not going through a Veth pair and the Docker Zero Bridge, but I'm going to suggest there are other options now that we'll talk about later that are, at least have similar performance characteristics. Map container mode is interesting. It's not really talked about a lot in the documentation, but it's where you start a single container, and then when you start a second container, you tell Docker to join it to the existing namespace of that first container. So for instance, if I started a container that offered a service on port 80, I could then start a second container that offered a service on port 8080 and tell it to join the same network namespace. Doing so means that both containers will see the same IP address, right? They're in the same network namespace. But that also means they can't offer services on the same port, right? If they both offered a service on port 80, just like you can't run a web server, on a bare metal server, you can't run two of them on port 80, it's the same thing. We're in the same network namespace. But that's an interesting option. There's what they call a sidecar sort of container mode, where you're joining things like logging engines and stuff into the same container so it can access things like through the local loopback address. In some cases, each container doesn't need its own IP. None mode is sort of interesting. When you specify a mode of none, Docker will still create a network namespace for a container, but it won't do anything with it. So it sort of creates an anchoring point for you to use. But then the expectation is you're going to build the network connectivity to get that container on the network. I know early on there were a lot of iterations around trying to get Open vSwitch working. So they would use the none mode. It's sort of using Docker as a container runtime without any networking functionality. And then they were building the connectivity manually to connect the containers to something like OVS. I'm going to encourage you here. It might be appealing to create your own networking model. You're gonna, when you get into this, you figure out that the container building the connectivity is not as hard as it seems. So it might be appealing to try to do this. I would suggest you don't. There's a lot of things container runtimes do on your behalf. We'll talk about some of that later, and it's generally not worthwhile. And if there is something that one of the built-in options of the container runtime you pick does not offer, I would look around, I would Google it. There are lots of companies that offer plugins that already solve some of this, and they're maintaining it for you. So I would look into that. I didn't mention this earlier, but native routing is definitely an option as well, right? So in our earlier example, if I just had one Docker host, I could have just told my upstream network, hey, 172.17/16 routed at 10.10.10.1, and it would have worked. I could tell Docker not to do, by default, outbound masquerade. I could not publish ports. And rather, Docker just ensures that the IP forward kernel parameter on the host is flipped on. The host just starts acting like a router, and I can natively route to every single IP. There's a service level called BIP, bridge IP, in which case I can tell Docker to use a not 172.17.00/16. So I could define unique networks on every host if I wanted to, and then just natively route to every single Docker host for the Docker Zero Bridge subnet. So that's definitely an option. Some of the higher level orchestration tools do use that model. Docker Network came around in version 1.12. It's a subcommand. A lot came with it, namely the ability to do user-defined networks. But we also got the option to connect and disconnect containers from networks dynamically. So if I wanted to create a custom network and then connect it to a new network to get new connectivity or disconnect it, Docker would take care of that for you, which was pretty hard because before When we started a container, we specified a network we wanted it on, and that was it. We'd have to kill it and restart it to get it to a new network. So that's a handy sort of option. The user-defined network options are bridge. A good example might be if you want to create a user-defined bridge that has that ICC parameter set to false. You could create a user-defined bridge that had that parameter and connect containers to it. Overlay was a big one for them. They call it multi-host, but essentially you're using an overlay to extend a network between multiple hosts. The big play for this, of course, is portability between clouds or disparate hosts where you want to extend a network. And I mentioned earlier a different option that was still performant. I would say that's Mac VLAN. That came with 1.12 as well. So Mac VLAN prevents the container's network namespace using the Mac VLAN Linux networking construct almost directly right on the host interface. And the interesting aspect that comes along with this is VLAN tagging. So I can have an interface on a host that I want to use just for container connectivity, doesn't have an IP, and I can create custom networks with .1q tags, put them on there, and then the assumption is my upstream trunk would have VLAN interfaces to use as gateways for those containers. But I can just trunk out, that's a means to do things like tenant isolation, things like that. So you have some means to get the traffic off the host in a tagged format. And I mentioned earlier why you should use some of the stuff if you can. Configuration state replay. If you guys have worked in Linux, you know all of the fancy networking stuff you do disappears when you reboot. Docker remembers all of it for you, as long as you do it through Docker. And it will replay it when the service restarts. So if it's creating these .1q interfaces for you to connect containers to, it replays all that config. So that's something I think I take for granted sometimes. It's actually really nice. It's sort of a reason to stick with it. So now I want to talk sort of briefly about two third-party plugins. Flannel was maybe one of the first ones when I started looking at container networking. It's a widely used overlay solution. It supports multiple different what they refer to as backends. The default is an overlay. It's a simple UDP-based tunneling mechanism. They have another mode that's interesting called host gateway, in which case they expect all of your hosts to be on the same subnet, and then Flannel will actually just create host routes for the allocated subnet. I'll talk about how it does that later. But it actually puts host routes in for every other host. So of course they need to be on the same subnet for that to work. There are other backends. They have some for some of the cloud providers. And then there's a native VXLAN backend as well. It is an etcd-backed solution, meaning that it requires a third-party key value store. And there's some interesting sort of prerequisites. This is sort of a theme we see with container networking to get things up and running. So what's interesting to me about Flannel specifically is how it interacts with Docker. It sort of interacts with Docker without telling it it's interacting with Docker. So Docker doesn't realize that it's using, by default, an overlay network to achieve container connectivity. So the setup is pretty simple. We have to have a key value store. In this case, it has to be separate from the nodes that we want to run Flannel across. And I say separate because I'm assuming you want to run it as a container. When I do lab work, I like to run the key value stores as containers just because it's simple. So if you're doing that, you can't do that with Flannel because we have to actually restart the Docker service after Flannel does its work. And restarting it, we're changing the IP address so the container would no longer be reachable. So in this case, the key value store should be separate. It could be a locally installed service. It just can't be a container within the Docker network you want to use. So we have the key value store. We put manually a key value pair in there to define sort of a global network scope. And then we configure the Flannel service on every host we want to talk to. The big thing we're configuring there is we're telling it where etcd lives. So then when we start the service, it will go out, it'll register a /24 scope out of the global scope. And then out of that subnet, it'll create a Flannel interface on the host. Then we have to tell Docker about it. So I mentioned that BIP flag where I can tell Docker to use a different subnet. Well, in this case, we just tell Docker to use the subnet that got allocated by Flannel, which it already has an interface on for the overlay. So it's a sort of backwards way of telling Docker about it. We're not really telling it it's using overlay, but it just sort of works. And Flannel provides some pretty nice constructs in terms of environmental variables and that kind of thing for you to use to make it easier to tell Docker about it. The last one, Weave. It's a really simple install because it's container-based. It's pretty slick. This one's been around for a while too. The interaction mode is more of a shim layer. The binary you download, actually then you use that to spin up the containers, and it in turn talks to Docker to spin up the container for you, so it's in a good position to do that. Interestingly enough, the overlay is additive here, so it maintains the Docker Zero Bridge connectivity for inbound and outbound stuff, but then it will create a new interface just for the overlay itself. They were the first to have DNS for containers before Docker had embedded DNS. And the big thing they like to tout here is that they don't have a reliance on an external key value store. So again, it's super simple, it just sort of works. And they do offer subnet-based segmentation and encryption, so if you're going across a public transport network, that might be a big deal for you. Interaction setup, I mentioned there's a CLI shim. So I can, instead of saying Docker run, I would say Weave run. Weave is then in a great position to provision the network where it needs to be. And then it will in turn talk to Docker to spin up the container. There's a network plugin as well. Docker has a networking model called CNM, Container Networking Model. So there is a Weave plugin for that if you're interested in using that. And there's also a local API proxy, which will talk to the local Docker service through. So the setup is much easier. We download the Weave binary. On the first host, we say Weave launch. And on every subsequent host, we just say Weave launch and specify an IP of an existing host. Doesn't have to be any specific one. You can go in any order you want. And Weave will do all the math to figure out the other peers and form a full mesh between all of them. So it's pretty simple in that respect. I think I'm over time. Can I keep talking? Okay, I'm going to keep talking. So looking forward. A lot of people ask me, if I'm interested in container networking, what I should start with, what I should be looking at. And I don't think this is specific to container networking, but I think most of us network engineers, if we're not doing it now, we should be spending more time with Linux. Linux networking, I think we're seeing a lot of the stuff, even that we're using physical appliances are all based on Linux, so I think having a good foundation there is important. Getting involved, I'm not a developer, I like to think I am sometimes, but the community out there that builds this stuff is really awesome, and they like to be interacted with. You don't have to be a developer to go out there on Slack or on GitHub and talk to them, ask questions. They really like it, in fact. And I would go talk to your app teams. I think, at least I have this fear once in a while that I'm going to get paged, and they're going to be talking about an IP address. I have no idea where it exists, and I have no idea what they're doing. And the theme with some of this newer networking stuff we saw at the VM layer, right, is app teams can do this on their own. They don't need to talk to us anymore. We don't need to turn on multicast for VXLAN to work on the upstream network, right? So I would go talk to the app teams. I would go ask if they're interested in, or if they're working on deploying a container-based solution. Because again, we know how the building blocks fit together. And I know I'm kicking the dead horse with that one, but I think it's really important that we're there to provide that sort of context. And lastly, don't worry, I'm getting sort of tired of the talk about you need to be a developer to stay a network engineer, or you need to be this to be a network engineer, and I don't think any of that's true. I think this is should be viewed as a new skill set, something to look into, something to move toward. That's it. Questions?
So have had a lot of experience with the sort of the VETH pairing method, bridging, mostly using Docker, which is sort of how we use VMs. And the advantage of it is that you can just attach anything that you want to do that generates flow or looks at PCAP or looks at sort of what's going on and get a sense of what's going on. Haven't played with really the overlay technologies. And I would say that some of the bridging and even layer 3 is not perfect. Sometimes you need to kick it. Generally, I found that layer 2 stuff is pretty horrible, and putting IP addresses on it makes it work much more robustly. But at least there is that level of instrumentation. So if you're trying to get in there and look at performance or do debugging, that you can do it. And I was curious with the various overlay technologies, how do they think about instrumenting for instrumentation? Where do you plug in, and how can you get copies of streams to turn into augmented flow or things like that?
Yeah. So I think you hit the nail on the head. That's a challenge, right? I think even the description I gave of how we connect a container seems pretty straightforward, but it's really not when you want to get that sort of information, right? Most cases you need to actually find, using simple tools like TCP dump is not even as straightforward as you want. Those don't always show up on a common bridge like Docker Zero. You instead need to find the VETH pair it's connected to get the traffic you need. So I'm not sure if there's a great solution for that yet. I know Weave has some tools out there around sort of the analytics piece of it, but I'd say that's a pretty kind of new space for it.
Thanks.
Yep.
I just wanted to make sure there wasn't something I was missing, because
I don't think so.
You don't see anything about deep instrumentation, you just have to figure it's not there. So.
Yeah.
Hi. You
Hi.
briefly mentioned multicast when you were talking about VXLAN. Can you talk a little bit more about multicast support inside the containers themselves and what the state of it is today?
No.
Excellent.
Do you have any considerations for IP overlap where we have shared IP space that basically collides? So if I have like a lot of business partners, B2B setups, how does Docker networking deal with that right now? Is it supported, or is it start to head down more of a custom, have to hand configure the IP mappings?
Are you talking about more from just the scale perspective, that we have more IP endpoints to deal with, or that you're interacting with a third party perhaps that's?
Tolerance for when I feed it IP addresses that overlap subnets. So if I give it 10.10.10.0/24 on one side, then I say, here's another interface, and by the way, it's got the exact same subnet. Does it have any tolerance for being able to figure that out, or allow me to give it mappings as a part of the native configuration? Or am I going to IP tables to straighten this out on my own?
Yeah, so I mean, the theme with all of this, right, is that container networking is not that much different than what we're dealing with today. So I mean, if you've got those problems today with your applications or your connectivity, they have to be solved somewhere. I think with containers, you probably have more options in terms of there are some service level parameters you can flip to tell Docker to do things like masquerade. But I mean, to Avi's point earlier, you know, if we're going to do analytics around this stuff, we don't necessarily want to start hiding the IP address behind things and stuff, right? So I mean, these challenges are not, I think, unique to containers. If you think they are, we should talk more afterwards.
Yep.
But there are some more tools. I think as we get closer into the operating system, we don't have to solve all these on the upstream network anymore. But it's the same iteration we saw with virtualized networking, right? It's the same problem. So I think that's still an issue.
Okay, thank you.
Yep. Anybody else?
Still on now?
Okay, thanks.